Let's look at getting energy out of a hydroelectric dam. Here's the world's best drawing of a side view of a hydroelectric dam. We've got 50 meters of water. Here's the dam's concrete, and then here's the turbine, and it's generating electricity as it lets water flow out into whatever other body of water there is here. An aerial view shows that the reservoir is 3 kilometers long and 2 kilometers wide at the dam face. I just made up these numbers just because they're nice and easy, not representative of any particular dam. So here's a question. How much energy can we get by draining the reservoir, letting all 50 meters of water flow out here? Now you might say, that's a bad idea. Usually we want to keep whatever lake we have behind the dam where it is, and that's usually true, but there's some interesting special cases called pumped hydro storage where we don't mind draining the reservoir behind the dam. We'll talk about that later. But let's go back to this question. How much energy can we get by draining the reservoir? The water at the top is at a higher distance from the bottom than the water in the middle, and so it has more energy that it can give us. So we can't just do this all at once. We have to say, let's think about things in kind of thin slices. So we're going to imagine thin flat slices, and that whole slice moves down and then out through the generator. So envision thin flat slices of water. And the point to them being thin is that they're all at approximately the same kind of altitude, and so everything in that slice of water moves basically the same distance down. Falling down, not really falling like whoomp, but gradually draining. It doesn't really matter how fast it goes in terms of how much energy it gives us. So how much energy does that first slice of water, let's say the top 1 meter slice of water, give you? Well, we're saying we're taking a slice of thickness 1 meter here. And what's happening with that slice? Well, energy is basically the same as work, or they're measured in the same units, which is force times distance moved, right? So work equals force times distance moved. How much force does it take or how much force do we get out of that falling, or how much would it take to lift it up? Well, we need force, that's mass times acceleration, right? Times distance moved. For that first slice of water, that's 50 meters. What's the mass of that water? Well, it's a big rectangular slice of water, right? So its volume is length times width times height. Length times width times height. And then we need to multiply it by the density in kilograms per meter cubed times the acceleration of gravity times 50 meters. What's the length, the width, and the height? Depends on how you label things, but we could say the length was 3 kilometers, the width was 2 kilometers, and the height, here we're talking about the height of this slab of water, so that's 1 meter. The density of water, so this gives us basically cubic meters. I mean, I have to throw in a factor of 1,000 here and there. Density of water is 1,000 kilograms per cubic meter. That's a metric ton. And this isn't just an accident. This is literally basically how a kilogram was defined. They said or you could say it's almost how, yeah, it's mostly how a kilogram was defined. That a kilogram is what 1 liter of water is. 1 cubic meter is 1,000 liters of water. And then 9.8 meters per second squared times 50 meters. So all of that is the work for that top slab of water moving down. That's the energy we get out of that top slab of water moving down. How about the second slab? It would be all the same times, well, it's not up quite as high, it's only at maybe 49 meters, etc., right? So altogether, what do we have? Well, we have all that stuff times 50 meters for the first slab, 49 meters for the second slab, 48 meters for the next slab. So we could add all that up. But here I'm using 1 meter, and really I should use narrower slabs, right? So each of them is at approximately the same altitude, like 1/10 of a meter, 100th of a meter, 1,000th of a meter, 1,000,000th of a meter, etc. So what I'm really saying here is that 1 meter is kind of like dy. It's the size of the stuff I'm dividing y up into. So I still have the 2 kilometers, 3 kilometers times 2 kilometers times dy times 1,000 times 9.8 times, and then what's this? The first slab is up here, the second slab is down here, the third slab is down there. That's basically the y value. And we're going to integrate that from 0 to 50 meters. So it's a little weird having dy there. We could rewrite it. So 0 to 50, 3 kilometers times 2 kilometers times 1,000 times 9.8 times y times dy. But it kind of more naturally comes from the physics formulas with the dy there. It all ends up being the same. So that's how we would say what's the total energy we get out of this big reservoir of water. Let's go take a look at where this actually happens. We'll switch to the browser. So there's this hydropower plant in Ludington, Michigan. Here's its reservoir, and here's Lake Michigan. So let's show where it is, kind of on the west side of the state. Here's a nice aerial view. There's the reservoir, and here's Lake Michigan. And here's a cross section. So they let water out of the reservoir down through the turbines and out into Lake Michigan to make electricity. But the cool thing is when electricity is really cheap, like late at night or maybe on the weekends, they can pull power from the grid, spin the turbines backward to pump water back up into the reservoir, and that saves energy from low price times, and then they can use it at the high price times. So that's how we can smooth out some of the randomness in like wind energy, or solar energy has this problem you might have heard of called night. So it's a way of storing energy. It's about like 75% efficient, so that's better than not at all, right? So in a system like this where you don't have recreational users or wildlife using the reservoir, it's okay to drain the reservoir a lot more than you would drain a regular lake, for example. One thing I forgot to mention in the paper and pencil work, the reservoir, in addition to not being a rectangle here, also doesn't just have a rectangular profile. It's kind of curved at the bottom, so we would have to account for how each slab has different length and width. So let's go back and write that down. So this is all assuming that the reservoir is straight-sided and flat-bottomed. Which is probably not true, but it sure made the math simple, right? If it wasn't, then these things right here would have to depend on the current y value. So then we'd have to have some kind of function that expresses that relationship of how much the rectangle, if it's a rectangle, how much its width and its length vary with the y value in the water column.